Welcome back to this series on architectural simplification. Today we'll be talking about multi-instance application architecture, which can be the painful side effect of a badly forecast, organic but siloed growth of an application. In the before and after scenarios, we'll be looking at an application that has been deployed across the US, the EU and Japan, all running locally on my machine as per the previous examples. In the before scenario, we'll have three siloed application architectures, one for the US, one for the EU, and one for Japan. A US user will use a US connection string to talk to the US database and application, and so on. In this scenario, as you'll see, we're open to things like config creep, which is the gradual, unintended divergence of configuration between applications, along with divergence of code and database. It gets very painful. In the after scenario, we deploy across the same three geographies, but using one database and one application. Each user in the real world would use a geographically aware load balancer to load balance their requests, and that would propagate the request onto the right application and hence database. The compose file for the before architecture contains a US database and a US service, which gets built by Docker. I'll show you the code in a minute. And it's the same for the EU and Japanese silos as well. Each have their own database and own application, all of which can diverge over time. The code across the EU, US and Japan is similar, but as mentioned, can diverge over time. So you'll see slight differences in the output of this, simply because of natural changes to the application over time. For example, each application might require different payment provider integrations. Klarna, PayPal, Adyen might be available in one region, but not in another. And the translation requirements of each application may differ. I would argue that they should be the same for each environment. The application should feel local to all users, regardless of their location. The application is basically just an API. There's a products endpoint, which takes a lang parameter from the query string and applies it to a query. I ask for all products, I join the translations table on, and I return the ID, the name, and the price. Now, to simulate the changes over time, developers of the Japanese equivalent have removed the need for translations, as most of their users use the application in Japanese. And in the US developers have decided that instead of returning the ID and price information, they would rather just return the SKU and the name. All of the regions have in some way diverged from one another, and I've seen this in the real world. Let's create the before infrastructure. I'll insert data for the US, which will look like this. I create a product table and insert products. The SKUs for these products are C1, C2, and C3. It's not uncommon for users in different locations to want to use different SKUs. I'll insert data for the EU, which looks like this. I create the same table and insert this time SKUs of 860U, 891A, and 874P. Completely arbitrary, but I've seen SKUs like this, and it's to demonstrate the divergence again of SKUs. And finally, I'll insert data for Japan, which looks like this. I create a product table, I insert data, this time the SKUs are C001, 002, and 003. Note that in this example, the Japanese developers have decided that they're only going to support the Japanese language, primarily because the majority of their clients use the Japanese language to interact with their website. Let's run a few curls now to see what the data looks like from these APIs. The 3001 endpoint talks to the US application, and it returns, as we configured, an array of products containing an SKU and a name. If I make the same request against the European endpoint, which is represented by 3002, asking for products to be returned in Spanish this time, I see that this time we've got IDs, names, and prices. Quite a different response from the US. And finally, if I make a request against the 3003 endpoint, the Japanese endpoint, I've got the ID, the name, and the price. This may have all seemed quite arbitrary, but I've seen much worse in the real world. I've seen 17 disparate instances of exactly the same application with different databases, different payment providers, different translations. Each upgrade of every application had to be performed in isolation with its own maintenance mode screen, etc. It's a real headache. You may or may not have noticed, but the IDs and SKUs for all of these products were different. Unless your product IDs and SKUs in a setup like this are all consistent, there's no way to get a consistent view of what a single product is in the system. Adding, updating, or removing a product in a setup like this is also problematic. If I want to introduce a new product into the catalog, let's say in this coffee example, a cortado, I need to do that 3 times, each with their own translations in each of the environments. A change to a database means 3 changes in this setup, and it only gets worse as I add more markets. If I want to make a code change or a code fix, I might have to do that in 3 places, depending on whether that code exists in each of those locations. In an infrastructure like this, the OpEx costs, the operational expenditure, are huge. And we haven't started talking about enforcing global constraints or rules for our application. the further the applications diverge, the harder that becomes. And as a developer, we like to dry out our code. Don't repeat yourself. Why is dry not acceptable in code, but sometimes acceptable in architecture? Which is why we're now going to move on to the after scenario, which will be a global equivalent of the same siloed architecture. I'll tear the infrastructure down. This time, our compose file looks like this. We have a US node, a European node, and a Japanese node. But this time we deploy 3 instances of the same service. They're all built from a global service, which looks like this. I connect to the database. I expose a product endpoint into which I expect a market parameter this time. That would be something like US, EU, JP. I still accept a language parameter, and then I return the data, the ID, the name translated into the language requested by the user, the SKU, and the price. I'll create the infrastructure. I'll initialize the database, which looks like this. I create a database whose primary region is EU Central 1. It could have been any of the other regions, but let's say this is a UK-based company and they have additional regions in US East 1 and AP Northeast 1, corresponding to the locations in the previous example. I then enable super regions. Super regions are primarily used to pin data geographically to regions. In this case, I've only got one region in each of the super regions, which isn't advised. In order to survive a single region outage in any of the super regions, each super region would need to contain 3 regions. In this example, I won't be able to survive regional outages. It's just to demonstrate a point. I create a product table whose locality is global, giving low read latencies to anyone wherever they are, at the cost of higher write latency. That's fine because the products table isn't a high write throughput table. I insert some products into that table. Ultimately, regardless of the number of markets, we're only dealing at the moment with 3 products: an Americano, cappuccino, and latte. I then create market-specific products for the above products, the primary key being the ID of the product, which references the product's ID, the market for that product, be that Germany, Spain, UK, etc. Whenever I see those 3, I'll assume that the region I want to physically place that data is EU Central 1, and so on. I store the SKU, which could differ between markets, and the price, again, which will differ between markets. I insert data into that table. For the Americano, I insert it into each of the markets with their own corresponding SKUs and their own prices. I then create the internationalization table, which contains all of the translations for all of the products. Again, this is a global table. Translations don't change that frequently, but they will be frequently read from. It's a read-heavy table, so it makes sense for this table to exist physically in each of the locations for low latency reads to all users. I'll create the infrastructure. I'll initialize the CockroachDB cluster. I'll enable enterprise features because I'm using multi-region functionality. And then I'll create the tables, regions, super regions, etc. and insert the data. I'll make a request to the US market and ask for products to be returned in Spanish. And I'm getting good read latencies. I could ask for that in any language. And because the product translation table is global, that's very low read latency join lookups to that table. I'll now test the UK market, this time for a German speaker. But that could be a Spanish or English speaker, it doesn't matter. And finally, the Japanese market. The behavior of each of these services is identical. The code for each of these services is identical, and they're all backed by one globally distributed database. Up to now, I've tested everything on my local machine, but you might be wondering, what does a global tables topology pattern look like in terms of real-world performance? I've set up a real-world cluster containing the nodes in my demo scenario. I have a cluster running in Tokyo, London, and North Virginia. And I'll connect to those now to give you an idea as to the performance of global tables for reads. First, I'll connect to my London node. I'll connect to my database. And I'll ask for products in the German market in the German language. And we can see that my read performance against the global table is between 4 and 7 milliseconds to get the data back. I'll now connect to my US node to simulate the experience of a US-based client. I'll connect to the database. I'll run the same query, but this time asking for US products in the Spanish language. And we're seeing really low 3 millisecond read times as well. I can change the language, it doesn't matter what language I run it in. If I ask for Japanese, I'll still get really low read times because it's a global table. And finally, I've connected to the Japan server to simulate the experience of a Japanese user. I'll connect to the database. And I'll run the same query, but this time asking for Japanese products in the Japanese language. And again, we're seeing single digit millisecond reads to these tables. I might be a Spanish speaker in Japan. It really doesn't matter. I'm going to get really low latency reads to these tables. So what we've actually achieved here, we've pinned market-specific product data and joined onto global tables. So we're taking data from geographically pinned product information. In this example, we saw German products pinned to an EU data center, US products pinned to a US data center, and Japanese products pinned to a Japanese data center. And we could join the global translations onto those tables without any impact to read performance. It's very easy to get into a situation whereby you end up dealing with multi-instance application architecture. If you start in one market and then need to expand into another market, rather than redesigning your application to work across both simultaneously, it can be tempting to copy-paste the infrastructure and deal with the consequences. This might be okay for 2 markets or possibly 3, but once you get to 10 or more markets, it becomes incredibly painful and risky to operate in that way. If you've got customers in multiple locations, it might be more appropriate to design your architecture to be multi-region from the start. There's uniformity in the way we've designed this global architecture. Business constraints and rules are easy to enforce because we're dealing with one source of truth. There's only one code base. If we want to integrate different payment providers for different markets, we can do so in one place. We don't have to crack open multiple code bases and make configuration changes everywhere. It can be operationally much cheaper to run a globally distributed database and application architecture. And it's also a lot simpler. The cognitive overhead of dealing with one database, one application is a lot lower than having to deal with multiple databases and multiple applications. Perhaps what I love most about multi-region application architecture is we've achieved centralized management of a distributed system rather than having to distribute our team to manage disparate infrastructure.